You ready? Okay.
Yes.
じゃあ、始めたいと思います。So please start your presentation. Yeah. 拍手で。
Okay. Can you all hear me? So today I'm going to be talking about building a scalable Python gRPC service using Kubernetes. And so it's not really actually written here, but basically this is the idea is microservices on a container cluster. So kind of have a lot of stuff to cover, so I'm just going to kind of get right into it. Let's see if it'll actually advance my slides. So just to give you an introduction, I'm Ian Lewis. I work for Google and here in Tokyo, and I'm basically what's called a developer advocate for the Google Cloud Platform. So like the closest analogous thing is an evangelist, I guess. But I talk to developers and to I'm a developer myself who talks to other developers and educates them and talks to them and gets feedback from them about Google Cloud Platform and how it works and what their needs are and that sort of thing. So I'm on Twitter and that sort of thing, so you can kind of check me out there. But what I'm going to talk about today, there's a lot of really buzzwords or keywords in my title, so I've got kind of a lot of things to cover. Probably a lot of these are new concepts to you because they're new frameworks and new libraries. So first I'm going to be talking about gRPC and concepts, just to give an introduction to what gRPC is and the concepts behind it. Then talk a little bit about gRPC in Python, how you use Python to do gRPC, and then talk about the containers and concepts, and Kubernetes concepts, and then actually do kind of a demo or whatever of actually running gRPC as a service in Kubernetes. So first I want to talk about gRPC and the gRPC concepts. So a lot of you are familiar with REST APIs, I think. Basically HTTP APIs that you access over a URL, and that URL represents the resource that you're trying to get. Whereas RPC is the thing that everybody kind of abandoned a long time ago because everybody used XML RPC, which was the problem was XML and not RPC. But RPCs are basically remote procedure calls. So that means basically you call a function or something like a function, and that gets executed on the server that you're actually doing the remote procedure call on. So gRPC is a framework for doing that, so it works over the HTTP2 protocol, which is a kind of a new protocol based on work that was done with the Speedy protocol. So I'm going to talk a little bit about what HTTP2 is, and then over that protocol, the actual sending of the data and the service definitions and things like that are actually done using a library called protocol buffers, which we use internally at Google. So I'm going to talk a little bit about HTTP2 and why it's good for things like RPC and why it was made. So HTTP2 is kind of a binary protocol, so it's not really great to use over Telnet, but it had a number of things in mind. One was to improve HTTP. So basically all the semantics are still there, like the request response semantics and headers and request body and all of that stuff. But the actual way that you send the requests is a little bit different. So one of the goals of this is to allow multiplexing, which is basically sending and receiving responses over the same connection. So a lot of with HTTP, you would have to, the browser, in order to make loading web pages and things like that fast, would have to access the server a bunch of times in parallel in order to get down the resources. Whereas HTTP2 can allow you to use the same connection to make multiple requests and then get multiple response back. and be able to do that in parallel. So that's what multiplexing is called. That's what's called multiplexing. It also uses things like header compression, so you can do things like actually compress the headers and not send them when they don't change and things like that. Prior to HTTP 2, every single request you would have to send like cookies and other things that you that wouldn't change every request, but you still needed to know because HTTP 2 was stateless. It also allows you to push responses to the client. So that means like when you load a web page, if you know that the client's gonna need JavaScript and CSS, you can send that along with the web page so that the web page or the browser doesn't actually have to request the JavaScript and the CSS and things like that afterwards. But things like server push and don't really matter when we're talking about gRPC, but things like multiplexing and header compression are really important. So next, I want to talk about protocol buffers. So now that we've gotten an introduction to HTTP 2, I'm going a little bit fast, but so protocol buffers is kind of a way of serializing data. So so you can think of it as kind of something similar to say like JSON or what's another good serialization format? So like so the types of language serialization formats like what in Python you would have pickle and things like that. This is actually kind of a language agnostic way of serializing data. And it also allows you to define things like services. So you can define some data and then you can define a service and say like, okay, I'm going to be sending this data over this service and things like that. But these are also kind of binary. So you know, there's really no love for Telnet here. But they're basically designed so that they can be parsed quickly. So you can serialize and deserialize the formats quickly, and they don't have a lot of overhead when you're actually making an RPC call. But they're also, especially in the new versions, they're also very flexible. So you can do things like add fields to it that are kind of optional, and then it will still kind of work without the extra fields for like old versions of of servers and clients. So you can have a little bit of flexibility with there to have like servers and clients that are running on different versions of your actual RPCs. Protocol buffers also supports code generation. So you define protocol buffers like a piece of data, and then based on that data, you can generate code in a lot of different languages. So say like Python or Java or Perl or whatever. And so you can actually, and those objects or those classes that you generated will have built into them how to actually serialize the data and things like that. The code generation also works for services. So you can, if you define a service and the data that goes along with it, it'll create the classes, and then it'll create the server that you actually need, and then you can just basically start the server and just implement the methods that you need to implement. And basically, all the boilerplate part of that would be generated for you. So I'll show that a little bit later. But protocol buffers looks basically like this. So you define like a message. So this is like basically analogous to a class in another language like Python. So you have this message called the person, and so this would actually generate into a person class. And then you have 3 fields in the person. So one's a string, one's an integer, and another one's a string. So you have a name, ID, and email. And then you give it like a field ID. So you give it a 1, 2, 3 as the field ID. And this allows you later to have a little bit of flexibility when you add and remove fields and things like that. So that servers and clients on different versions will actually be able to parse the messages that you've created. So this is how you actually define something, a service, and there's a lot of kind of plugins and interesting things you can do when you're defining services. But this is a pretty simple example. So here's a greeter service. It's not a very good name for it, but basically you could say like maybe you're authenticated with the server, and you can just say get me, and that'll return the person data for the person that's logged in. You can obviously add parameters to your function and pass that in to the server, which the server uses to process the request and return a response. But this is basically how you would define a service. So this is something similar to like creating a class and then having a method inside of the class called getMe that returns a person. So that's pretty easy. So with gRPC and Python, so gRPC is kind of an open source project. It's based on what we used to do inside of Google called it's based on a library that we use internally at Google called Stubby, and Stubby is basically, they gave it that name because it generates code for you for services. But gRPC is essentially a new kind of generation of that. It's hosted on GitHub, and it has a lot of the it has all of the implementations for each language in there. So Python's in there as well. But currently, gRPC is kind of, at least for the Python version, is still kind of in an alpha stage, and so it's pretty new, and it's not particularly easy to install at this point. So I'm going to go into a little bit about how to do that. The easiest way to do it right now is if you're going to be using a gRPC service and you don't need to actually do development, you're just going to install the things that are required for a service that you're going to run, then you can just install they have instructions there to install a package, basically a Debian package that you can install for a library, and then you can install the Python package that they have released. And that package is called gRPC.io. I'll show that in a little bit later. But if you're going to actually be doing development, that you're going to actually want to, you'll need a few other tools in order to actually do development and actually create a gRPC server. And so that's what I'm going to go into, how to do that. And so what you need to do is basically just fork or clone the repository and then and build it. So you can basically just run make to build it, and then and install it, and then after you've created it, you'll also need to install this protocol buffers. The protocol buffers version 3. So protocol buffers version 3 is also on a GitHub repository. And so you, after you've built both those projects and installed them, you can then write your services like the protocol buffers files that we saw a second ago, and then actually generate the code using the gRPC Python plugins. So here you can kind of see that that we're using a protocol buffers plugin to actually generate code. So here I'm using the Python plugin, but if you're going to be generating something like Java code, you would use the Java plugin, etc. But protocol buffers, the compiler by itself without a plugin just compiles it. So it doesn't really, it can't actually generate code for you unless it has the proper plugin. You can kind of create multiple like gRPC. You could create your own gRPC library based on protocol buffers that's not gRPC. So in that sense, like it has this kind of like plug-in architecture going on here. And so what we do is like compile that, and it spits out some Python code. And I'll kind of show a little bit about how that works a little bit later when I do the demo. And so once you've done that, you can import the library that you've that was generated, and actually implement the methods in your server. So that's like kind of an introduction to gRPC and how that works, and all of the kind of nuances about how to actually use it. Now I'm going to talk about containers and Kubernetes and how you actually would deploy something like that. So we're going to kind of go off into kind of DevOps land for a little bit. So containers are something that's kind of new, but I kind of want to talk a little bit about, kind of contrast what containers are like compared to what people do currently, pre-containers, essentially. So a lot of people are developing web services or web servers kind of with an architecture kind of like this. This is a pretty typical architecture. So you have like a web server, or a set of web servers, and they have a cache tier and a database tier, and maybe some backend batch processing. And so the way that you would actually deploy something like this without containers is, maybe deploying your web servers on VMs and having your cache servers on another set of VMs, and maybe your databases on another set of VMs. And so there's some issues that kind of go along with that. And even prior to like using VMs, you had people, would deploy things on like shared machines. So, running the same, running your web server and your database server and stuff like that on a single machine. And what this does is basically makes it so that you don't have very much isolation, so that if your database like uses up too much memory, then your web servers don't have enough memory to run. And so your website gets slow, and you don't really have a way of kind of boxing them off or to separate them out. You're also using kind of a common set of libraries. So like if you need a particular version or a particular library for one of your apps, and then another app needs a different version of that library, or an incompatible library, then you can kind of run into problems. And maybe even if they say that they're compatible, maybe the libraries aren't compatible. You don't really necessarily know, and so you're kind of you're running it without kind of having that isolation there with the libraries that you're depending on as well. And so it's kind of highly coupled to the environment that it's running in. If you're running just on a regular OS, then people will just write their log files to a specific directory, or like do all kinds of things that aren't going to be easy later to like scale your application or break those things up into a different architecture. So people kind of mitigated this a little bit by using virtual machines. They give you some isolation, because you can say this virtual machine has this much memory and this much, and uses this number of cores and things like that. But they're kind of expensive and they're inefficient. They have overhead for CPU for the kernels or the guest OSs, and as well as memory for the guest OSs. They're also a full operating system, so you need to boot them up like a regular machine. So they take on the order of tens of seconds to start up. So doing things like scaling your service in and out, like if you're going to run a microservice in VMs, like that's going to be really kind of bloated and overworking, or like going to be too much for what you want to do. You want to be able to like scale up and down pretty easily. The VMs are also hard to manage. You have to manage the operating systems that are running on it and things like that, and you just have like a lot of them, and you have to manage the operating systems and what libraries are installed on each and every different type of application. So your database servers might have these libraries installed, and your web servers might have these libraries installed. So that can be kind of hard to manage. So containers like kind of solve some of these problems. and I'll talk a little bit about how they do that. But first, I want to step back a little bit and kind of talk about how Google kind of sees containers. We kind of see it as like a balance between running things like infrastructure as a service, or VMs, and running platform on a platform as a service. So with VMs, you have like this kind of flexibility, but not very agile. So what that means is you can run pretty much anything. So it's pretty flexible. You can run any library you want or any kind of application you want, but they're not very agile in that you have to manage them and manage the apps that are running on them. You have to write all your DevOps scripts and Ansible scripts and things like that, and actually manage the servers. And so it can be kind of difficult. Whereas platform as a service is kind of on the other end of that spectrum, where it's really agile in that you can deploy to it, and like it can maybe even scale automatically for you, or it can start up the servers and schedule your application to run on some servers for you and set up the networking. But it's not very flexible in that you're limited to the types of things that platform provides you. So the APIs and things like that. So if you're familiar with things like Heroku or App Engine, the APIs that are kind of provided for you to use are kind of limited and are perhaps kind of proprietary to that platform. So we see clusters kind of, or containers kind of sitting in the middle of that, in that you can install pretty much anything you want on a container in a container image. So you can install Redis or whatever application you want to run, but you also get a little bit more agility in that you can deploy your applications much easier. And you don't really have to think about which machines everything's running on, and perhaps you can even work on a system like Kubernetes that sets up things like networking for you and all of that. And so deployment becomes a lot easier. And so so that kind of strikes a balance between the platform and platform as a service type of offerings and infrastructure as a service. So containers work like this. They're basically apps that are kind of enclosed in their own little world. And so containers are based on a set of features in the kernel called C groups and namespaces. And what C groups do is they allow you to set process groups or create process groups that can only use a specific set of resources like memory or CPU. And then also you can use namespaces, and what namespaces do is they kind of make your application look like it's the only one running on the server. So they have it. You create a namespace, and so for that process, and then the process gets its own list of, say, like process list and mounted file systems and all of that stuff. So it looks like it's running on its own little machine when it's actually just inside of a container. And so when you run things like that, you can actually have isolation between the apps because the apps can't actually see each other. And you also have the isolation in terms of file systems and resource usage, but you don't have the problems with the VM where you have the entire operating system running inside of it. So you don't have the overhead of actually running another operating system inside there. And you also don't have the issue of the startup and shutdown times. And that's actually a pretty big one because when you kind of scale up things like microservices or scale down microservices, it becomes pretty important that you can start and stop the applications pretty fast. So this is like, the, Google appeal slide that says, we run everything in containers, and we do. We run Gmail, web search, maps, everything. Basically all of our databases, all of our Gmail, all of our web search, even things like Google Compute Engine VMs run in containers. They're implemented as KVM processes that run as a container inside of another machine. So it's kind of a little bit of an inception kind of thing going on there. And we launch 2 billion containers a week. So we do this quite often. We've been doing this for about 10 years, using container technology. So we have quite a bit of containers running at Google. And the reason we use that is for performance, for repeatability. Running the process is pretty repeatable. And then and for other things like quality of service, accounting, and portability. So I'm going to kind of blow through Kubernetes, but so Kubernetes is an open source project that we released 1.0 recently, and it's pretty popular. We're also working with a number of other companies on it. Companies like Red Hat, Mesosphere, CoreOS are on here. But I kind of want to talk a little bit about a few of the concepts of Kubernetes. So one is called a pod. And pod basically is just a group of containers that run on the same host. And they kind of look like a single logical machine. And each one gets its own IP address. So Kubernetes kind of does its own magic networking. And so it creates its own, it creates an IP address for that pod. And then the pods can actually kind of talk to each other over localhost. So you can think of the pod almost like a logical machine, but pods are also the smallest or the most granular way that pods get scheduled on a cluster. So when you actually run a pod on a cluster, they always get scheduled. The containers that are in the pod get scheduled together on the same machine. So this is really good for things like that need to work together really well. The canonical example is using a web server and like a content manager or a Git pull kind of thing. So you can pull from your Git repository and update your local files, and then have your web server serve up those files. And so you can have you can kind of do a Git push to deploy that kind of way. And you can kind of mix and match those kind of small services together very easily. The next concept that I want to talk about is a replication controller. And these are, what this is basically a controller that controls the pods that you are deploying. So you can basically tell Kubernetes that you want to run X number of pods, and you want to use them to run this image and stuff like that. So you give it a template, and then it can use that to start up the number of containers that you want to start up. And you give it things like labels and stuff, which I'm going to talk about in a second. But this is really nice because you can use it to do rolling upgrades as well as scaling up and down your service. So you can also give labels to your replication controller template, and so that will tell it to attach labels, and you can use those to select your pods later, and then do new things with them. This will allow you to do things like, you can select the pods, but you can also potentially in the future do things like create dashboards to show that the pods, like what resources that each type of pod is using and that sort of thing. And then lastly, I want to talk about services, and services are a way of creating a logical IP address or a logical endpoint for your API service, and then having that endpoint be routed to each of your individual pods. So here I can have a service that has a label selector which selects on the FE label, and then what that'll do is when you connect to the service, it'll actually route your traffic or route the network traffic to each of the individual pods, kind of like a load balancer would. And so what you would do is you would have a replication controller over here that creates your pods with that particular label, and then use a label selector on your service to actually connect to those pods. And that's how you would define a single service. So that's what I'm going to do. So now that I've kind of gone through that, I'm going to try to put it all together and give you an idea of actually how to run a gRPC service. So let me actually turn on mirroring so I can So here I'm kind of logged into a machine that I've got up and running, and so what I have here is a service that it's basically the greeter service that I was talking about earlier, but it basically does like something like a hello world kind of application. And let's see. So if you look a couple directories up, and you go into the protos directory, in here it actually has the protocol buffers files that you use to implement the service. So in this particular one, so here we've got this service greeter that says say hello, and you send it a hello request and it returns a hello reply. And in the request you just basically give it a name, and in the reply it gives you a message back. So it's basically you give it a name like hello Ian, or you give it a name like Ian, and it's going to send you a hello reply that says hello Ian. So it's a pretty simple service. So if we go back to Python and we go back to the hello world directory here, we'll see the client and server, and then here I've already generated this PB2 file is the actual generated code. So if I go here and I say to see, yeah. So here's like the actual command that you would use to generate it. So here's like the protocol buffers, compiler, and like all of the options and stuff like that. So if I actually hello world.
そろそろ時間なので。
Okay.
はい。
So if I actually generate this, let's see, like it'll actually show it here, and you can kind of see that this is the actual service, but like basically you import that hello world PB2 and then run the service using that particular channel. And then what you can do is actually bundle that up into a Docker image, and then deploy that to Kubernetes to actually run the service. And so let's see. If I go to this demo, you can see like that I have a replication controller definition, and these are actually written in YAML. Run, and it has an image that I've created for the Hello World app, as well as a service definition. So you can use the let's see, Kubi control command to actually create that in Kubernetes. So actually I actually don't have it installed on this machine. I have it locally. But basically, so I'm kind of out of time, but if you have like questions about how to actually go ahead and deploy that, then I can kind of answer your questions a little bit later. So thanks a lot.
ありがとうございます。ちょっと時間が押したので質問は個人的にやっていただければと思います。
Yeah, so I'm going to be like kind of around. So if you have any questions about anything that I talked about, then you can just find me like outside here.
ありがとうございます。Thank you very much.